Now, what we are used to, and what we've looked at in stats already from stats 1 is the binomial distribution. That is the only that's the only distribution that we've actually looked at as like a named distribution. You did look at discrete random variables, where you looked at lots of different possible discrete distributions, but none of them were really named. So there is this split between different distributions. They are either discrete or they are continuous. And binomial was one of the discrete distributions. Okay, that's the one that we know about. One that we have discussed, but we haven't met properly yet, is the normal distribution. Now, the normal distribution is something that we will be coming up to relatively soon. But today, of course, we're looking at the Poisson distribution, and it is another example of a discrete distribution. So, need to make sure that you understand what the Poisson distribution is. Now, there are several links with the binomial distribution, and we're not out of the water with binomial. It's not just a stats 1 topic. Okay, so what I'd like you to do is, with the person next to you, could you write down 5 things that you could remember about the binomial distribution, or things that you remember doing with the binomial distribution? Okay, let's go through the list. Right. Binomial distribution is down to either success or failure. Okay, binomial, bi meaning 2. Okay, so there are 2 possibilities. The trials are independent of one another. Okay, so one roll of the dice will not affect the next roll of the dice. Okay, the number of in each trial. The number of trials that we have in the binomial is n, and the probability of success is p. P for each case is going to remain constant throughout. So the dice, as I'm rolling it, won't suddenly become bias halfway through my trials. This was something that was given to you in the formula booklet. The expected value, okay, the mean of the binomial, and you multiplied n and p together. You were also given the variance, var of x, as np times 1 minus p. Okay, we needed to remember those. They're in the formula booklet. Now, the formula for it used NCR, okay, the combinations formula, times the probability of success to the power of r, how many times you want the success to happen, times by 1 minus p, the probability of failure, to the power of how many you have left. Okay, so that was the formula that we utilised, and the tables that you were given in the back of the formula booklet are just probability of x being less than or equal to r. Okay. So what I'm going to do is I'm going to give you a problem that involves the binomial distribution. An executive airline deliberately overbooks its daily flight to Dublin because it knows from experience that not all passengers who book a flight actually arrive for that flight. It is assumed that each passenger arrives independently of the others. 8 passengers have booked a day's flight on a 6-seater plane. It is known from past records that the chance of any booked passenger arriving for a given flight is 0.3. Okay, this is a regular practice of airlines. I have fallen victim to it myself. It's very, very, very annoying. Okay, so there are 5 questions below. Work with the person next to you to see if you can answer all 5. Let's do B first. So, if we go into B, how many passengers do you expect to arrive on average? Then that's E of x. So, E of x is going to be 8 times 0.3, so 2.4, okay? And make sure that you don't round that, okay? Variance, well actually let's do variance then. So var of x is n times p times 1 minus p. Okay, and I believe that's 1.68. Right, now once you've got E of x as being 2.4, can you remember what the binomial distribution actually looks like when you do it as like a stick graph? So if you've got something that's like the probability of 0.3, then your bars, so this is your probability, these are your x's, the bars are going to be higher towards the left, okay? So this will be skewed, this will have positive skew. So remember skew and the direction of it, you're looking at the tail, so this is positive skew because the tail is going towards the right. So this would be at 0, 1, 2, 3, 4, 5, 6, 7, 8, okay, for example. So if you're looking at what is the most likely, you're looking for whatever the highest bar is in your distribution. Now, you're not going to need to work out the probability of x being equal to 0, 1, 2, 3, 4, 5, all the way up to 8. You won't need to do that, because x equals 8 is definitely not going to be the highest bar. If you use the E of x as like a little identifier of it being 2.4, so I'd be thinking, right, it's either going to be 2 or it's going to be 3. Okay, so it's really either one of these two that I'm looking for. So if you use the binomial distribution, so NCR times p to the r times q to the n minus r, so you use the actual formula to get those two, you get 2 as 0.2964 and 3 as 0.2541. Okay, so 2 is 0.2964, 3 is 0.2541, and so 2 is actually your answer to part A. If you're being asked what's the most likely number of passengers to arrive for the flight, it's not 2.4, okay? It's going to be an actual number of passengers, but the expected value can be a decimal. Now for D, how many passengers must arrive for the aircraft to be full? Or, remember there's 8 passengers potentially, so 6, 7 or 8. Find the probability that the aircraft is full. So we know that it's going to be full if there's 6, 7 or 8. So you're looking for the probability of x being greater than or equal to 6. Okay, so that's the probability that we need to find. Now remember, your tables can't look up greater than or equal to. So this is one take away, the ones you don't want, from 0 to 5. Now this one you should be able to look up in your tables. Okay, so with n is 8, p is 0.3, looking up 5, so we get 0.9887. So that's 0.0113. So when you think, oh, the aircraft company, or the airline rather, think, well, the probability of everyone turning up is just over 1%, then it makes sense, perhaps in their eyes, to put on a 6-seater flight for one where you could potentially have more people turning up. But the probability of that happening is so low that they can take the hit financially. Okay? So when it happened to me, being stopped at the gate, just about to board the flight, and then you're stopped and go, no, sorry, the airplane is full. I was then in a position where I then was put up in a hotel for the night. Had to go out of the airport, put up in a hotel, and then I had to get a next plane the next day with monetary compensation. So here's the binomial distribution for this problem. So it looks kind of similar to what I drew. Obviously I put the highest bar at 3, but the highest bar is actually at 2, as we saw from the table, okay? So, the Poisson distribution, okay? It is inherently linked with binomial. They do have a lot of similarities to them. However, the binomial distribution has a difference in that it has a fixed n, a fixed number of trials. The Poisson distribution does not. The Poisson distribution is all about a rate. And so it can take anywhere from 0, 1, 2, 3, 4, 5, up to however many you want. Okay, it just keeps on going. So there's no upper limit for the Poisson distribution. Now, it happens quite a lot. It will occur quite a lot in everyday life. So you could use it to look at the number of cars that will pass a point in a minute, or the number of radioactive atoms that will decay in an hour, or the number of misprints that will occur on a page of a book, or the number of plants that grow in a square metre of a field, or the number of a certain type of cell in a cubic centimetre of blood. Okay? And all of these examples are examples of rates. Okay? The number that are appearing in a certain interval. So in a minute, in an hour, on a page, in a square metre, in a cubic centimetre. Okay? So the Poisson distribution is governed just by that rate. And we refer to that rate as lambda. So whereas the binomial distribution had 2 bits to it, it's got the n and the p, the Poisson distribution only has lambda. Okay? So that lambda will represent the rate, the average number of events of things that occur or are present in a particular period. Let's get rid of this. So how do we write it? Because we said that, x has that x tilde b np. For Poisson, we write that x is a Poisson distribution with parameter lambda. Okay? Now what is important is that you understand the 3 things that you're looking out for to make sure you can identify that a Poisson distribution fits it. And you will need to make notes on this. Okay? So, if x represents the number of events that occur in a particular space or time, then x will follow a Poisson distribution as long as it fits these 3 bits of information. Firstly, that the events occur randomly and are all independent of each other. Okay? So if you're looking at cars passing a particular point in a minute period, okay, then the fact that one car's gone past doesn't necessarily mean that it's going to drag 2 more with it, right? So the probability of one passing will be independent of another. And the events should be random. The events happen singly, so one at a time. So the cars are going to pass me one at a time. Okay, there's not going to be two cars passing me at the same time. Although yes, if you were like on a motorway, then that could potentially happen, but you could determine, like, with a very good camera which one has passed first. And the events happen on average at a constant rate, and that's your lambda. And this is the formula that goes with the Poisson distribution. Okay, so the probability of x being equal to a particular value r is equal to e to the minus lambda, so that's our e that we all know and love, times lambda to the power of r over r factorial. Okay. So, random and independent, singly, constant rate. Okay? So, you need to make sure that you are clear on those 3 points. So, random and independent. 2 is singly, and 3 is at a constant rate. Grab mini whiteboard for me, please. I'm going to give you 3 situations, and I'm going to ask you to determine, is it a Poisson distribution or not? Based on those 3 bits of criteria. So could it be modelled by Poisson distribution or not? Does it fit those 3 pieces of criteria? Okay, yes or no, that's all I'm looking for. So here's your first one. The random variable x represents the number of 6s thrown in 20 minutes of dice throwing. Okay, 5, 4, 3, 2, 1, make a choice. Let's see what we think. Okay, people have gone for yes, that's a Poisson. Okay, so this is, you would expect the 6s to occur randomly. They will certainly be independent of one another. One dice getting a 6 will not affect another. And they'll occur one by one at a constant rate. Okay. The variable x, the random variable x, represents the number of grains of sand in a cubic centimetre of a large beaker full of water. On average, there are 750 grains of sand per litre, but the beaker has been standing for a few minutes. Okay, 5, 4, 3, 2, 1. Not sure. Oh, right. You disagree. Right, I see. Okay, so where does it... Most people went for no. Where does it fail then? Which of the 3 criteria does it fail? Yes, I think the key thing that you said there is that because it's been standing for a few minutes, the sand will have dropped to the bottom. Okay, so if you're thinking about the number of grains of sand in each cubic centimetre of water, then it's no longer going to be random and independent, is it? Okay. Now you said at a constant rate, okay, but it really depends upon the cubic centimetre that you look at. So they won't be distributed randomly or independently anymore, okay? In fact, because they've been dropped to the bottom, you'll also have the situation that I expect some will be clumping together, in which case they won't be appearing singly. However, if you had the situation where it had been well stirred, right, so you'd stir the water and then you're looking at the situation, then this should be a Poisson distribution. Because you've spread them around, they should now be appearing singly, and they should now be distributed randomly and independently. Okay? So it's down really to the context, and we need to be careful of that. So let's say, here's a problem. A shop sells wedding dresses at an average rate of 1.5 per week. The random variable x represents the number of wedding dresses sold by the shop in a given week. state the probability distribution of x. Well, you first need to think about, well, is it a Poisson distribution? Okay, that's really what I'm getting you to think about here. Is it random and independent? So this is a question to you guys. Is it independent? More likely to be, right? It's more likely to be independent. It's unlikely that because someone's got in to buy a wedding dress, then somebody else will go, oh, that looked nice on me, and I go in and buy one as well, right? That's not necessarily going to be the situation. Singly, is someone necessarily going to go in and buy 2 wedding dresses? It's unlikely. It could happen, yes, but it's unlikely. At a constant rate, well, we've been given that it's an average rate of 1.5 per week. So we would be expecting that, yes, this could be represented by a Poisson distribution, and we just say that x is a Poisson distribution at 1.5. Okay? So that's how we would deal with that. Now I also need to make sure that we're happy using the formula. So this thing up here. So here is a table that I'd just like you to fill in these first 3. Now obviously this probability table goes on and on and on, okay, forever. I just want you to fill in those first 3 boxes to make sure you're happy using that formula. Okay? Just a bit of formula practice. Okay, so plugging in those values, we should be able to get these 3, 0.0608, 0.1703 and 0.2384. Okay? So that's just plugging in using the formula. So if I had this situation and I asked you what's the probability of x being equal to 2, it's 0.2384. Okay? So what does this distribution look like? Well, here it is. Okay? It kind of looks binomial-like. Okay? Similar to it. However, although it's still got that kind of similar kind of shape to it, and it's got, in this case, this tail, this just goes on forever. These probabilities get smaller and smaller and smaller and smaller and smaller. Remember, all the probabilities have to add up to 1. Okay? But they're still there. They're just very, 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 very small. Okay? So it'd be like saying, you know, if I was looking at that problem of the cars passing me in a minute, and I found that the rate was 2.8 per minute, what's the probability of 100 cars passing me in a minute? Well, it's very, very, very small, okay? But I can choose, like, the number of cars. It could be 70 cars. What's the probability of 60 cars? What's the probability of 5 cars, okay? So the actual number that I want to actually appear, that there's no limit to that. So here's 1. Here's the probability distribution for lambda is 1. Here's 4, just to kind of give you a difference. And here's 7.5. So as the lambda increases, you can see that the bars in general get smaller and it gets a little bit more spread out. Okay, so here's a question for you. The number of defects in a wire cable can be modelled by the Poisson distribution with a uniform rate of 1.5 defects per kilometre. Find the probability that a single kilometre of wire will have exactly 3 defects and a single kilometre of wire will have at least 5 defects. So I want you to have a quick go at A, okay, and then pause there and I'll show you how we're going to deal with B. So we should get 0.1255. Now for B, at least 5. So the probability of x being greater than or equal to 5. Okay? Now Poisson distribution is discrete, so it works in exactly the same way as binomial. So to work out greater than or equal to 5, I've got to do 1 take away the probability of x being less than or equal to 4. Okay? Now I don't want to have to work out less than or equal to 4 by hand. So thankfully, your tables for Poisson start on page 18. Okay, so main things to take away from this today is that, firstly, the Poisson distribution is governed by just that one parameter, the rate, the lambda. In order to be Poisson, it needs to satisfy those 3 conditions. You need to have those 3 conditions memorized. The formula is given to you. Okay? You can use it to work out individual probabilities, and there are tables to work out less than or equal to, just like binomial. So if you're looking at binomial Poisson, they are very similar in style. Okay?